Hi, this is the solutions for problems from our book, section 2.2, numbers 15 through 32, part 2 of the book problems from section 2.2. Number 15, we're looking for the limit as x approaches, see 3 from the positive side of x over x minus 3. Now this would be pretty easy to do if you graphed this in your calculator and just looked at the graph. It would make it like problems that we did in section 2.1, where you just look at the graph and see which side it's approaching a vertical asymptote from. Maybe we should back up and say, how do I know that it's got a vertical asymptote before I graph it? Well, if you plug in 3, I get 0 on the bottom and 3 on the top. So a number over 0, any number over 0, means that we have some kind of limit that is undefined. But would like to, since this is a one-sided limit, would like to be more specific and say whether it's positive or negative infinity. So how do we do that without a calculator? If you're thinking to yourself, well, who cares? I just used my calculator. I definitely am interested in you being able to do this without a calculator. So if you did all these with a calculator, you might want to watch the first couple here and then go back and try some of these without a calculator. That was the idea. And if that wasn't clear, I apologize for that. So this is how we're going to approach this. How we're going to approach this. Get it? I didn't even mean for that to be funny, but how we're going to approach this, because it's a limit, right? It's approaching 3. So, sorry, I thought that was funny. Maybe you didn't. So when we plug in 3 here, numbers, this is numbers approaching 3 from above, right? So those are numbers like 3.1, 3.01, getting closer and closer to 3, but bigger than 3. So what are we going to have here? On the top, we're going to have a number that's very close to 3, and on the number, on the bottom, we're going to have a number that's very, very close to 0. It's 3 minus 3. But since it's something that's a little bit bigger than 3 minus 3, I'm going to say that it's a positive version of 0. In other words, it's something that's very small but positive. And that means that this is going to be approaching positive infinity. So that's the idea. That's how you figure that out without a calculator. Number 16, how about the limit as x approaches 3 from the other side, x minus 3. So that's the same thing, it's the same function here. But now I'm approaching 3 from below, so these are numbers like 2.9, 2.99, getting closer to 3 from below 3. So those numbers that are a little bit smaller than 3 minus 3, that's going to be something very close to 0 but negative, right? Because I have something smaller than 3 minus 3. And so that's going to approach negative infinity. And then to bring it all home here, they're going to ask us, how about if we don't specify which side? So we check both sides. We have a positive infinity and negative infinity, so that means if I graphed this, I'd be approaching a vertical asymptote up on one side, down on the other, positive infinity on one side, negative infinity on the other side, so that limit does not exist. And then really all of these are versions of non-existence. So it's not technically wrong here to say does not exist, but since it's a one-sided limit, we can include more information here by saying it's positive infinity or negative infinity, and here that it does not exist because these do not agree, the two sides. Let's see, 18, we've got the limit as x approaches 2 from the positive side of x over, and then the bottom is x squared minus 4. I'm going to go ahead and factor that. Oops, there should be a 2 there, sorry. And the reason I'm going to factor that is it's easier to tell what's going on with the signs if I do factor that. So on the top, I've got something that's getting very close to 2. And then on the bottom here, I've got something that is 2 from the positive side. That's a little bit bigger than 2, so that's a positive version of 0. Right? Something that's a very tiny, tiny bit bigger. And then on the bottom, I have something that's just about 4. So if I check the signs here, I've got positive, positive, positive. So that means I'm approaching positive infinity here. Right? Multiplication and division, you just count up any negative signs, and if there's an even number, for example, 0 is an even number. If there's no negative signs, then we're going to be approaching positive infinity. 19. I'm going to check the same one from the other side. What's the limit as x approaches 2 from below? X over, and again, I'm going to write that in factored form, so it's easier for me to check the signs. So I get the same thing, something that's just about 2. On the bottom, I've got something now, since I'm approaching 2 from below, that number minus 2 is going to be very, very small, close to 0, but negative, right? Like 1.9 minus 2, for example. And then here I still have something that's very close to 4, and I've got a positive, and a negative. That gives me a negative here. So hopefully that makes sense to you, why we would like to factor those and how that makes it a little easier. And I'm going to do the same thing here. As x approaches 2, well, I don't need to plug anything in here because I've already done both sides. So the two sides disagreed, so this limit does not exist. I can't say positive or negative infinity because they disagree. Number 21. What's the limit as x, sorry, this time I'm using y, as y approaches 6 from the positive side, y plus 6, or y squared minus 36, that's y plus 6, and y minus 6. You might notice here that because I have that factor in common, those are going to cancel out. So that's really just a matter of checking y minus 6. And that's going to give me 1 over, if I'm a little bit bigger than 6, this is going to be something very close to 0, but above 0. So that's a positive infinity. As y approaches 6 from the other side of this, I'm just going to write it like this, 1 over y minus 6, because I've already done that work. So now I have 1 over, when we approach 6 and we have numbers that are just a wee bit smaller than 6, that's going to give me a negative, something that's negative and very close to 0. So that's going to approach negative infinity. And guess what number 23 is? What about the limit as y approaches 6 without specifying here? So again, I'm going to write out my factored canceled form. And since these did not agree, the limit does not exist. And it looks like in the next 3 we have the same little game here, checking both sides. I'll move up to here. So number 24, I've got the limit as x approaches 4 from the positive side, 3 minus x over x squared minus 2x minus 8. So I'm going to go ahead and factor that. That's x minus 4 times x plus 2. And this is the same game we talked about in the first half of these problems. If you plug in 4, you can see that you get 0 on the bottom. So I already knew for free that x minus 4 was going to be one of those factors. Not that x squared minus 2x minus 8, that's not really that hard to factor, but it is nice to have that little tip off there that x minus 4 is going to be one of those factors. So let's see with my signs now. On the top I've got 3 minus something very close to 4. It's going to give me something very close to negative 1. On the bottom, 4 from above, so that's very close to 0, but it's positive since I'm approaching 4 from above. and then 4 plus 2, something very close to 6. So I've got negative and 2 positives, so since I have a 0 on the bottom, that's going to approach negative infinity. You just stop here for a second and talk about, if you object to the fact that this is approaching 4, and I'm plugging in 4 and just saying that it's 6, I know that since the bottom's equal to 0, that it's going to be a positive or negative infinity. So if it's troubling to you that I'm plugging in something that's approaching 4 and I'm saying that it's 6, it's something that's really, really close to 6, but for the purpose of just checking the signs here, that 6 is certainly good enough. Same with the negative 1. And, at any time, if there's something that happens in one of these videos that you don't understand or you want to talk about more, please do not hesitate to ask me about it. The idea of the flipped classroom, where we have all these videos that you can look at outside of class, is that it frees you and me up in class. It frees you up to work on calculus, and it frees me up to, during class time, to be the sort of resident calculus expert who is available whenever you need me to ask me questions. And you should never, ever, ever be shy about that. That's my job, to answer your questions, help you understand what's going on. All right, so here, same thing. We've got 4, but we're approaching from below. So these are things that are a tiny bit smaller than 4. So smaller than 4 minus 4, that's going to be very close to 0, but negative. And then this is going to be 6-ish. So negatives cancel out. And on this side, I get positive. So number 26, when I just look at the limit as x approaches 4, but I don't specify which side, that's going to be a does not exist, because those don't agree. All right, so that might seem a little bit redundant there, but it's good practice to do that. Get the idea of how to check those signs. All right, so I think we've broken free from those little sets of 3 here. Let's see what we have now. We've got the limit as x approaches 2 from the positive side, 1 over the absolute value of 2 minus x. So what's going on there? So here I'm plugging in something that's a little bit bigger than 2, so that means 2 minus something a little bit bigger than 2 would be very close to 0 but negative. But since that's an absolute value sign, so that's going to get rid of that negative sign, and we'll be approaching positive infinity. And if they asked us about the other side, because of the absolute value signs, the other side would also be positive infinity. And if they did the whole 3-way thing, like 24, 25, and 26, that means I could have positive infinity, and then here, instead of having to say does not exist, I could say it's also positive infinity, because they agree. But they didn't ask us that. So we'll move on. Number 28. Approaching 3 from the negative side, 1 over the absolute value of 3, of x minus 3. So this is really the same thing here. This is a little bit smaller than 3, so that would be negative inside here, but since the absolute value signs are there, it doesn't matter what the sign is in here. It's going to get changed to positive. So once again, I get a positive infinity. It wouldn't be, I know you're supposed to do these without your calculator, it wouldn't be a terrible idea, just for the sake of curiosity, to graph some of these, and after you determine what these limits are, to go ahead and see what they look like. You don't have to do that for all of them, but not a bad idea to help your intuition for these things. See what's going on. All right. This is a little different now. So how about this one? This is back to a 0 over 0. If I plug 9 in, 9 minus 9 is 0, square root of 9 is 3, minus 3 is also 0. So how do I deal with this? There's a couple of things you can do. I don't remember for sure whether I showed you an example like this or not. Maybe I did, maybe I didn't. If you just let your algebra instincts loose on this, you might have an instinct to, since there's a square root there, square root minus something, to multiply by the conjugate. This is a little trick. We're going to use some in Chapter 3 also. So here, if I multiply the top and the bottom of this by the square root of x plus 3, that's going to help us out here to be able to cancel things out. Now, I'm not going to FOIL this out or do any kind of what someone might call simplifying. I'm going to leave it like this because it's going to be much better for us to leave it in that form. And then here, this is the difference of two squares. The reason why we multiply by the conjugate is to get rid of that square root sign. And you see what that did for us is it got an x minus 9. You can see we knew that 9 was causing the problem, but this gets it to really show up very clearly on the top and bottom in the same form. And look at this. I did the thing that I want you not to do. I wish I could say that I did that on purpose, just to demonstrate. But I genuinely forgot. You have to have this here, right? So then I can cancel those out. And now I can just plug in the 9. The square root of 9 is 3 plus 3 is 6. What do you think it would look like if you graphed this and looked around x equals 9 at what's going on with this function? What do you think it would look like? Let me think about that for a second. Is there a jump in the graph there? Is there a vertical asymptote? Is there a 0 on the bottom, or is there a hole in the graph? You could pause the video there and maybe just think about that for a second. Maybe just think about it, and you could also graph that and kind of snoop around the graph there. Why don't you pause the video and do that? So I hope you did actually pause the video and do that. What you should see is the graph really looks exactly like this. It looks like the graph of the square root of x plus 3. It's just that there's a hole in the function at 9. And with your calculator, probably you can't even really see where that hole is because of the way the calculator plots pixel by pixel. If you made a table, you would see that everything looks all fine, except when the 9 shows up in the x column, it's going to say error in the y column because of the dividing by 0. So there's a hole in the graph. This looks like a graph where everything looks fine, but then there's a hole at 9, and then it keeps going. And what is it getting closer and closer to? It's getting closer and closer to 6. So what we're doing here when we cancel out, we're just sort of canceling out that hole, and we're figuring out where that hole is. All right, almost done. Number 30, if you didn't get 29 and you kind of understand that, then definitely pause and try number 30 now because it's very similar. I do that a lot in these videos. I ask you to pause and try to figure something out, and I hope you do actually do that. It's not because it's not for my benefit. It just engages you more in the whole problem-solving process here. So I'm going to do the same thing, except I'm not going to make that mistake and leave out the limit here. So on the bottom now, multiplying by the conjugate, that turns this into the difference of two squares, 4 minus y. And then there's my 4 minus y on the top. That's great, because that's my problem spot at 4, so that's going to cancel out now. That's good news. And once those cancel out, I can just plug in the 4, and that's 2 plus the square root of 2, which is usually 4. Just kidding, it's always 4. Okay, last two problems. Got some piecewise defined functions here. So, let me just bring this up here. So I've got this function. It's equal to x minus 1 for x values that are less than or equal to 3, and it's 3x minus 1 when x is greater than 3. We could call this, if you want to use fancy math language, this is a piecewise linear function. It's piecewise because it's defined in these two different pieces, and we say piecewise linear because both of the pieces of it are straight lines. The big question would be, do they link up or not? You could have a piecewise function where you got one piece and then another one that comes like this or something, or you could have a piecewise linear function where you've got one piece and then the other one links up, like the hole in this one is filled. They perfectly match up to each other. How can you tell without doing like a lot of graphing and a lot of stressful kind of work? Well, you can just plug 3 into both pieces and see if they agree there and see if you get the same point. So we could just do that quickly here just to see. If I plug 3 into this, I get 2. So the point 32 is like the little point on the end, and I know that there's a point on the end here because of the equal sign there. And this one, I plug in 3, and I get 9 minus 7. That's also 2. Now, if you're objecting to the fact that I'm plugging 3 into this because there's no equal sign here, like, wait, you can't plug 3 into this piece. There's no equal sign. That doesn't make any sense. What I'm doing is I'm finding the hole. I'm finding that place where it stops being this, right? But it does go all the way up to that and then have that open circle. And it is an open circle, but the open circle is at 3. So 3 plugged in here, that will tell me where the open circle is. So these ones link up. So the limit as x approaches 3 from below, 3 from below we would plug into this side, so 3 plugged in here, that's 2. And then we also check 3 from above, that's this piece. These are the values that are greater than 3. And 9 minus 7 is also 2. And that means that the limit as x approaches 3. Since they agree, I can say that that limit is 2. I'm sorry I didn't rewrite those, but I just wanted to have that to refer to there. I don't want you to write the answers in your textbook when you get a textbook, so this is unusual that I have a photocopy of this. But maybe nice for these piecewise ones, just so we don't have to recopy them. And besides, I was almost out of space there. All right, last one. So same idea. When t is greater than or equal to 0, this is the rule for the function. So I could plug 0 in here, and I get 0. And then when t is less than 0, this is the rule for the function. It's this straight line. And when I plug 0 in here, I get negative 2. So notice right off the bat that those do not agree. So as I approach 0 from below, this is the below 0 rule. So I get negative 2. I'm getting closer and closer to negative 2. And as I approach 0 from above, this is the rule for things that are greater than 0. I get closer and closer and closer to 0. I know that just by plugging 0 in there, which means that if I just say t approaches 0, since these don't agree, this does not exist. And maybe just real quick, we could graph that. So this function g of t is equal to t squared for values that t greater than 0. So make a graph of g of t and t. Those would be the names of my axes, right? It's the same as y and x. They just use different names for those. That shouldn't stress us out. And when t is greater than or equal to 0, it's just the parabola t squared. But when t is less than 0, it's the line t minus 2. So that has a y-intercept of 2, and it's never equal to 0. It's as close as you want, but that's going to be that open circle there. Closed for this piece because of the equal sign, and open on this end because there's not an equal sign. and then it's a line with a slope of 1. So the graph would look like this. And you can see on this side, approaches 0. Over here, it's approaching -2. And that means if we just say what's the limit as t approaches 0, it does not exist because they don't agree. Let's show you something real quick on your calculator. I don't know if you ever learned this, how to graph piecewise functions. Let's see if I can remember how to do this myself. So, can you make a piecewise graph like this with your calculator? You can. So this is how you do it. On one side I want x squared, and then I'm going to put a slash there, like a division sign, and I'm going to put curly brackets. I hope I'm doing this the right way. We'll see if this works. And then I'm going to say that's for x values that are, and then the inequality signs are in the test menu, second math, right here. It says test. Those are the logic tests. And that's for greater than or equal to 0. And then close curly brackets. And then on the other piece of my piecewise function is x minus 2. And then I put a slash there. I know we usually think of that as a division sign. Here it's just functioning as sort of a separator. And then I put curly brackets, and this is for values of x that, back to the test menu, are less than 0. And let's see if I remembered the right way to do that. And hopefully, if I go back to my standard window, yep, that's how you do it. And then you can see those two pieces. That agrees with what we did here. So you can make those piecewise graphs. Of course, this is all stuff that I would like you to do without a calculator, but it is possible to make piecewise graphs in a calculator. So there you go.